The reason some toggle or limit switches are rated 20 amps 125 volts but only 10 amps 250 volts is because of the way the switch is constructed. Specifically, it is due to the switch's contacts. At lower voltages, such as 125 volts, the switch contacts are able to handle a higher current, such as 20 amps. However, at higher voltages, such as 250 volts, the switch contacts are not able to handle as much current without overheating. This is because the higher voltage causes a greater amount of arcing across the contacts, which can lead to premature wear and failure. To prevent this, the switch is designed with a lower current rating at higher voltages. This ensures that the switch contacts will not overheat and fail prematurely. As for why the switches do not simply have a wattage rating, this is because the wattage rating is dependent on both the voltage and the current. For example, a switch rated for 20 amps at 125 volts has a wattage rating of 2500 watts, calculated as 20 amps times 125 volts equals 2500 watts. However, the same switch rated for 10 amps at 250 volts has a wattage rating of only 2500 watts, calculated as 10 amps times 250 volts equals 2500 watts. Therefore, it is more accurate to rate switches by their voltage and current ratings rather than by their wattage ratings. This ensures that the switches are used within their safe operating limits. Consider what happens at the point of contact within a switch as it opens and closes. There are two main factors that limit the current a switch can handle: voltage and heat. Firstly, voltage is a measure of electrical potential difference. It's the force that pushes electrons through a circuit. The higher the voltage, the greater the potential for electrons to jump across a gap, such as the gap between the contacts of a switch as it opens. This jumping of electrons is called arcing. Arcing erodes the switch contacts over time, reducing their lifespan and potentially causing the switch to fail. The higher the voltage, the more pronounced the arcing effect. Secondly, heat is generated by the flow of current through the switch contacts. The higher the current, the more heat is generated. If the heat exceeds the switch's ability to dissipate it, the switch can overheat and fail. The materials used in the switch contacts, their size, and the overall design of the switch all contribute to its ability to handle heat. Now let's relate these factors to the different ratings. A switch rated for 20 amps at 125 volts can handle that level of current at that voltage without excessive arcing or overheating. However, when the voltage is increased to 250 volts, the arcing becomes a more significant factor. To limit the arcing and prevent premature failure, the maximum current rating of the switch is reduced to 10 amps. In essence, the switch is designed to prioritize longevity and safety over maintaining the same high current rating at a higher voltage. It's important to understand that wattage is simply a calculation of voltage multiplied by current. While it represents the total power the switch can handle, it doesn't directly address the specific limitations imposed by voltage and heat. Therefore, providing separate voltage and current ratings gives a more complete picture of the switch's capabilities and limitations. Think of it like this: consider two different types of pipes. One pipe can handle a large volume of water to low pressure. The other pipe can handle a smaller volume of water to high pressure. Both pipes might deliver the same total amount of water over time, but they are designed for different conditions. Similarly, a switch can handle a certain amount of power, but its voltage and current ratings dictate the specific conditions under which it can safely operate. In summary, the reason for different amperage ratings at different voltages comes down to managing arcing and heat within the switch. Higher voltages increase arcing, requiring a lower current rating to maintain safety and extend the lifespan of the switch. Providing separate voltage and current ratings offers a more precise understanding of the switch's operational limits compared to a single wattage rating. When selecting a switch for a particular application, it's crucial to ensure that both the voltage and current ratings meet or exceed the requirements of the circuit. Using a switch outside of its rated limits can lead to premature failure, electrical hazards, and potential damage to equipment. Here's an analogy involving water pipes to further illustrate the point. Imagine you have a water pipe rated for a certain flow rate and pressure. If you try to force too much water through the pipe, high current, it might burst due to the stress. Similarly, if you increase the water pressure beyond the pipe's rating high voltage, it could also burst. The pipe has limits on both flow rate and pressure, and exceeding either limit can cause problems. Electrical switches are similar. They have limits on both voltage and current, and exceeding these limits can lead to failure. In the case of a switch, exceeding the voltage limit can cause excessive arcing, which erodes the contacts and eventually leads to failure. Exceeding the current limit can cause overheating, which can also damage the switch. It is also important to consider the type of load the switch will be controlling. Some loads, such as inductive loads like motors and transformers, can create voltage spikes when the switch is opened or closed. These voltage spikes can further exacerbate arcing and reduce the lifespan of the switch. For inductive loads, it's often recommended to use a switch with a higher voltage rating than the circuit voltage to provide an extra margin of safety. Moreover, the construction of the switch plays a significant role in its ability to handle different voltages and currents. Switches with larger contacts, better insulation, and more robust mechanisms are generally able to handle higher voltages and currents. The materials used in the switch contacts also affect its performance. Some materials, such as silver alloys, have better conductivity and arc resistance than other materials. When selecting a switch, it's important to consider the application, the type of load, and the construction of the switch. Choosing the right switch for the job will ensure safe and reliable operation. To reiterate, the practice of rating switches with different amperage values at different voltages stems from the physical limitations of the switch components, particularly the contacts. The fundamental issue is managing the effects of arcing and heat generation. Firstly, arcing occurs when the switch contacts open or close, especially under load. The higher the voltage, the greater the potential difference across the contacts, and the more likely electrons are to jump across the gap, creating an arc. This arc is a miniature electrical discharge that can erode the contact material over time, leading to switch failure. Secondly, heat is generated due to the resistance of the contacts and the current flowing through them. The higher the current, the more heat is generated. If the heat isn't dissipated effectively, the switch can overheat, potentially damaging its components and leading to failure. Now, let's explain why wattage isn't the primary rating factor. While wattage, which is voltage multiplied by current, represents the total power the switch can handle, it doesn't fully capture the independent effects of voltage and current. For example, a switch rated at 2500 watts could be rated at 20 amps at 125 volts or 10 amps at 250 volts. Both scenarios result in 2500 watts, but the stresses on the switch are different. At 250 volts, the arcing is more severe, necessitating a low current rating. Consider the analogy of a garden hose. The power, wattage, is analogous to the amount of water delivered. Voltage is similar to the water pressure, while amperage is similar to the flow rate. A certain amount of water can be delivered with high pressure and low flow, or low pressure and high flow. However, the hose material might be more susceptible to bursting under high pressure, regardless of the flow rate. Similarly, a switch is more susceptible to arcing at higher voltages, regardless of the current, necessitating a lower current rating. The switch's construction and materials are designed to handle a specific combination of voltage and current. Larger contacts, better insulation, and arc-resistant materials can improve the switch's ability to handle higher voltages and currents. However, there are practical limits. It's often more cost-effective to direct the current at higher voltages than to significantly increase the size and cost of the switch components. Therefore, providing separate voltage and current ratings gives a more accurate representation of the switch's capabilities and limitations. This allows users to select the appropriate switch for their application and avoid exceeding its ratings. In summary, the different amperage ratings at different voltages are due to the need to manage arcing and heat generation. Higher voltages increase arcing, requiring a lower current rating to ensure safe and reliable operation. While wattage represents the total power the switch can handle, it doesn't fully capture the independent effects of voltage and current, making separate voltage and current ratings more informative. Always adhere to the voltage and current ratings specified by the manufacturer to prevent switch failure and potential hazards. Moreover, it's worth noting that standards organizations like UL Underwriters Laboratories and IAC International Electrotechnical Commission set the testing and certification requirements for switches. These standards specify the tests the switches must pass to be rated for a particular voltage and current. The tests typically include endurance tests, where the switch is repeatedly operated under load, and overload tests where the switch is subjected to higher than rated current. Switches that pass these tests are certified and marked with their voltage and current ratings. These ratings provide assurance that the switch is safe and reliable when used within its specified limits. In the context of switch design, various factors influence the voltage and current ratings. Firstly, the contact material significantly impacts the switch's performance. Materials like silver cadmium oxide offer high conductivity and arc resistance, making them suitable for higher voltage and current applications. Secondly, the contact size and shape are crucial. Larger contact surfaces reduce contact resistance and improve heat dissipation, allowing the switch to handle higher currents. Thirdly, the contact pressure affects the electrical connection. Higher contact pressure reduces contact resistance and improves conductivity. Fourthly, the insulation material plays a vital role in preventing voltage breakdown. High-quality insulation materials can withstand higher voltages without arcing or tracking. Fifthly, the switch's mechanism, including the spring and lever system, affects its operating speed and contact bounce. Faster operation and reduced contact bounce minimize arcing and improve switch life. Sixthly, the enclosure design influences heat dissipation. A well-designed enclosure can effectively dissipate heat generated by the switch, preventing overheating. Seventhly, the manufacturing process ensures consistent quality and performance. Precise manufacturing tolerances and careful assembly are essential for reliable switch operation. When selecting a switch, consider the specific application requirements, including the voltage, current, load type, and operating environment. Choose a switch with appropriate ratings and features to ensure safe and reliable operation. Always follow the manufacturer's instructions and applicable electrical codes.